The second model we're talking about in Chapter 17 is called the binomial model. And what the binomial model is allowing us to find the probability of is some number of successes in a fixed number of Bernoulli trials. We flip a coin 10 times. What's the likelihood that we're going to get 4 tails, right? The number of trials is fixed. It's 10. The number of successes is identified. It's 4. And we're looking for the probability of how many ways we can distribute that 4 amongst the 10 trials, and adding them all together. It's a way to, it's kind of a combination of the multiplication rule and addition rule kind of squished together in a way that we don't really have to do either, but we kind of get to work around a lot of unnecessary button pushing, really. And it's specified by, or it's defined by the number of trials and the probability of success. The number of trials is still n, and the probability of success is still p. So we're going to see something when we define the model that we're using. We're going to be given binom n comma p, and the n is going to be a whole number. The p should be a decimal of some sort. And the look of the binomial model is kind of clunky. This idea here is the C, where you see this right here. That's accounting for all the ways we can take, in 10 trials, distribute the 4 successes. The 4 successes could happen on the first 4 trials, the last 4 trials, the first, third, and 7th and 8th. It can happen a lot of different ways. This is a combination of 10 things taken 4 at a time, or n things taken x at a time. These numbers get very, very big, and they account for all the possible ways we can distribute those successes over the trials. When you're doing this, we're going to use the calculator for all the heavy lifting. We're not going to do this by hand, because this function here, the combination function, is kind of a buried option in our calculator, and it would be an inordinate amount of button pushing and time consuming to do this. So we're just going to let the calculator do the heavy lifting, but we're going to dress up the problem like we're doing it by hand. So here's an example. We're using our Tiger Woods problem from before, right? What is the probability of finding 3 Tiger Woods cards in 10 boxes of cereal? We know that the probability of success for finding a Tiger Woods card is 0.2. So our model would be binom 10, 0.2, right? We would dress it up like this. We would show it like this. We'd say the probability of x, because x is our number of success, or our number of successes, so x is equal to 3. 10 combinations 3. Now sometimes you will see just a 10 over a 3 inside parentheses with nothing in between it. It's like a fraction with the bar taken away. That means the same thing. 10 combination 3. We're just writing it. We're not calculating it. 0.2 to the third, 0.8 to the 7th. Whether you show that as 10 minus 3 or just 7 is really semantics. So the likelihood that in those 10 trials you get 3 successes is 0.2013. How did we get that? We definitely want to use a calculator on this one. And we're going to go to our second vars function, which is exactly where we would go to find our normal model. Now we're using our binomial model there as well. And if you're in there, you'll probably see the geometric model as well. We'll talk about the geometric model later, more in class, in person. But the binomial model, you'll definitely want to use a calculator for, and you need to give it 3 bits of information. What does the calculator need to know to do this? Well, it needs to know the number of trials, 10. It needs to know the probability of success, 0.2. It doesn't need to know the probability of failure, because it can figure it out from the probability of success. And then it needs to know how many successes. And basically, it's taking those numbers and plugging it into that formula. As you can kind of see from there, it just does it for us. And it's all a push of a button. You do have to remember your Remember your commas. But in this case, we are looking for precisely 3 successes, so we're going to use PDF. The P, it's not does not stand for precise. I think it stands for probability. But it's the that's how I kind of remember. If we're looking for precisely some number of trials, we're going to use PDF. And there we have it, about 20% chance. If we change the question slightly to what's the probability of finding 3 or fewer cards in 10 boxes, well, then that gets to be a little more time consuming, because that could be 0 Tiger Woods cards, 1 Tiger Woods card, 2 Tiger Woods cards, or 3 Tiger Woods cards. We'd have to do that same process that we did for 3 successes for 0, 1, and 2. That would be kind of cumbersome, but that's really what we're finding here. When we find that 3 or fewer, that's why it's less than or equal to, we find the probability of 0 successes, 1 success, 2 success, and 3 success, and add them all together. It would look like this were we to do it by hand, and this is what we want to still dress up, right? It looks way more complicated than it is. Once you get in the habit of doing this, and this is in your formula sheet, the binomial model is in your formula sheet. So you don't have to commit this one to memory, but you do have to commit the idea of, well, what are all these things? Now, there's only 4 things that we would need to add up: 0, 1, 2, and 3. We can show the write-up for 0, 1, 2, and 3 and include them all. Oh, there's double decimal there. Sorry about that. But if you had, like, what's the probability of 15 successes in 100 trials, well, then you don't want to write it out 15 times, right? So if you have a large number of successes that you're looking for, you can do the first couple, do the ... and then do the last one, and that's fine. That will suffice. That will communicate that I know what to do for this. But note how these numbers are changing, like the subscript and the second subscript of the combination and the exponent of the probability of success are always the same, like the 1 and the 1, the 2 and the 2, and so on and so forth. And that should help, hopefully, remember, to do all that. Now, how to set this one up on the calculator is slightly different. We look here and we say we still go second vars, binom, but now we're not dealing with a precise value. We're dealing with a group of values. It's everything 3 and fewer. Then we're going to use the CDF function, which is cumulative distribution. When you're using the CDF, you have to be really careful what you're putting in here for this last one. The first two numbers are always the same, the number of trials and the probability of success. But what you put in there for that last one really depends on the wording. This is 3 or fewer, right? So 3 is an option. That's why we include 3. If we wanted to find less than 3 successes, we would still write it as less than 3, but we would put a 2 in there instead of a 3, because we wouldn't want to include 3. So when you're using the CDF, that last number is the last one you want to include in the group that you are collecting, right? So if you want successes 0 to 3, include 3. If you want 0 to 2, put 2. Okay. But that's, and make sure you'll still get a probability, whether you use the wrong one or not. And it's not always going to be obvious that you've got a wrong answer. So just make sure you're really paying attention to what the probability that you're looking for is, and that you're using the right binomial function in your calculator. Okay. A question that you might get both in this unit and in the inferential unit is, what would we expect our successes to be in this number of trials? Well, we've talked about expected value in chapter 16. We talked about it when we were dealing with geometric models, and we're going to talk about it now with binomial. And as usual, the mean behaves just like we think it's going to behave, right? So if we have 10 trials and we have a probability of success of 0.2, it shouldn't be all that complex to say n times p. however many trials times the probability of success. Standard deviation is the square root of n times p times q. If you're dying to know the derivation of that, I believe it does get explained in your book. I don't think they're going to ask you for it on the test. So if you really, are into where these things come from, I think it's in the book. I'm not going to go through it here. So in our case, right, and that should be 2 because we're only doing 10 trials. I don't know where that 20 came from. Sorry. So that should be I'll fix that here. 10 times 0.2. Sorry about that. Times we would expect 2 out of the 10. And did I screw up the other one too? Probably, right? Yeah, where'd that come from? 10 times 0.2 times 8. So I'll fix that right here. 10 times 0.2 times 0.8, 1.26. Right? Sorry about that. Must have had a different problem in there at some point. Right? So we would expect there to be 2 successes if we bought 10 boxes, and that makes sense with the standard deviation of a little over 1.25. Right? Now, why would we care about the mean and standard deviation? The normal model can be used to approximate the binomial distribution if the success failure condition is met, and this is one that is going to keep coming back around. So this one, you want this one to make sense. You want to understand this one. The success failure condition is pretty straightforward. If we can expect at least 10 successes and 10 failures, we can use the normal model to approximate the binomial model. Basically, we're going to take n times p, and if it's greater than or equal to 10, and n times q, and greater than or equal to 10, then we can use a z-score to calculate the probability of any particular number, a number of successes. Usually better for larger samples, right? The bigger the n, the better for using the normal model. We could not use the normal model for what we described with the Tiger Woods, right? N times p only gives us 2. We would expect 2 successes. That's not enough, right? So we wouldn't be able to use the normal model for that. Because we'd have to use the binomial model. But if you've got a big sample, if we're talking about thousands, you could use the binomial, the normal model, calculating a z-score and plugging it into normal CDF to approximate the binomial. It's not going to be exactly the same, but it's going to be a pretty good approximation. Okay. So that's our second model, the binomial model, which gives us the probability of some number of successes in a fixed number of trials. There's lots of ways they can dress this up. They do like this type of problem on the AP test. They always seem to have one of these on there. So whatever practice you can do on this will be beneficial. And please let me know if you have any questions. I hope this helped.